folks, welcome to another set of ICP video notes. Today we're going to learn about electricity. So first off, what is electricity? You've already learned that electrical energy is the energy of the movement of charged particles through a wire. To be more specific, electricity occurs when there are negatively charged particles, or electrons, that are moving through a wire. We transport electricity through wires, and often through a series of circuits, transform that electrical energy, that electricity, into some other type of energy, such as thermal energy or mechanical energy. In order for electricity to flow, you must have a complete circuit. A circuit is just the system of wires or the path of wires that electricity will flow through. To have a complete circuit, you cannot have any gaps in the wire. For example, you can have a broken wire, or a dead battery, or a broken light bulb. Because once there's a gap in the circuit, you no longer have electricity flowing. There are two types of simple circuits. We have series and we have parallel. In a series circuit, all of the components, light bulbs, switches, resistors, batteries, they're all in a row. They're all in one loop, per se. There's only one path for the electricity to flow through. In a parallel circuit, there are multiple paths or loops that the electricity could flow through. We call those branches. So in a series circuit, there's only one path the electricity can take. If we have a broken light bulb, that electricity will not flow because that one path that it has to take is now broken. There's no way for the electricity to get through. In a parallel circuit, however, since there are multiple loops that you could go through, if you have one light bulb broken, that just means that the electricity gets shut off to that branch of the parallel circuit. It will still flow through the other branches. Electrical engineers spend a lot of time drawing circuits, not just building them. A circuit diagram is like a blueprint for how to build a circuit. You could also think of it as a map for any future electricians that will be looking at your electrical circuits so that they can see how everything's hooked up together. When we draw circuit diagrams, we use these symbols here to my left to represent the different components you could have in a circuit. There's a whole bunch more, but we'll just focus on these very basic ones. You need to know these, so make sure you have them written down somewhere. All right, let's draw a couple circuit diagrams. We'll do the same components, but we'll do one in series and one in parallel. So for our series, let's say we want one battery, one switch, one resistor, and one light bulb. Start here, do a battery, do a switch. Oh, we could do a resistor here. Keep going around, let's do a light bulb. And that's your circuit. That's a series circuit. Notice how they're all just in one loop. There's only one way for the electricity to flow. If we want to do that in parallel, we could start out the same way. Here's our battery. Maybe put a switch here still. But you'd want a branch coming off this way and a branch coming off this way. Let's put the resistor on this branch and the light bulb on this branch. And there you go. So this one's parallel because if we cover up the bottom part, say our light bulb goes out, the electricity can still flow through the top. Or if our resistor goes out, we can still have electricity going this way, as long as the switch is closed, of course. It's not enough just to know how everything's hooked up. We also need to be able to describe the electricity that's flowing through the circuit. This is really important because if we have too much electricity, we'll blow out a light bulb. Or if we have too little electricity, our light bulb won't work at maximum efficiency. There are three aspects of a circuit that we can analyze in order to get a better understanding of the electricity flowing through it. And that is current, voltage, and resistance. Electrical current is simply the electrical flow. To use an analogy, if a hose is the wire and the water is the electricity, your current is how fast the water is flowing through the hose. We measure current in amperes, or amps for short, and the label unit we use is a big capital A. Next, we have voltage. Voltage is the electrical pressure. Without this pressure, the electricity wouldn't have a reason to flow. To continue the analogy, you could think of this pressure as being maybe the pump that pumps your water through your faucet, which your hose is attached to. If that pump were shut off, the water wouldn't be flowing through it. In electrical terms, the pump might be a battery or some type of electrical generator. So in this case, voltage is the strength of the pump. How hard is that pump pushing the water? How hard is that battery trying to push the electricity? We measure voltage in, well, you guessed it, volts, with a big capital V for our unit label. Lastly, we have resistance. Resistance will counteract the current and slow the electricity down. This can be affected by the type of material the wire is made out of, the diameter of the wire, or the length of the wire. To continue our analogy, the wider or the larger diameter hose you have, the more water is able to flow through it. Or maybe a shorter hose would take less time for the water to flow through than a longer hose. We measure resistance in ohms, which is represented by the capital Greek letter omega, which kind of looks like a horseshoe. Now I know you were afraid of this happening, but guess what? We have some variables, so we've got some equations to figure out. Ohm's law helps us to describe electricity by putting the voltage, current, and resistance all in one easy-to-read equation. In this case, V is equal to voltage, R is the resistance, and I is the current. Basically, the more resistance we have, the less current there is, or the more voltage we have, the more current there is. You're welcome to copy down these three equations and or the triangle that's here. If you're using the triangle for the equation, you just cover up whichever variable you're looking for, and what's left is your equation. So if you cover up V, then that's equal to I times R. Or if you cover up R, that's equal to V divided by I. So let's do a few example problems. Okay, so our first problem says that our current is 60 amps and our resistance is 2 ohms, so find the voltage. First step is to write down what you know, and then write down the equation you're going to use. Since we're looking for voltage, we'll use V equals I times R. Plug in our numbers, and you get that the voltage is equal to 120 volts. Our second problem says we have a voltage of 12 volts and a resistance of 0.5 ohms. So again, write down what you know. Since we're looking for the current, we'll use the I equals equation. That says I equals V over R. Plug in our numbers. And you get that your current is equal to 24 amps. Our last problem says that we have a voltage of 1.5 volts and a current of 0.5 amps. What's the resistance? So we take the R equals equation. In this case, R equals V over I. Take our 1.5 volts divided by 0.5 amps. That gets us about 3 ohms for the resistance. Well, that's all for today, folks. I hope that you're now able to draw and build simple circuits and use Ohm's law to describe the electricity in the circuit.